Hello everyone. In this session we're going to study active filters, active pass filters, active stop filters, band stop filters, band pass filters using the op-amps. So in previously what we studied three types of different op-amps configurations. It's inverting, non-inverting, and the unity gain op-amps. So now we're going to study how to use these op-amps to actually build the filters. So as you already maybe know or gonna know, there is like three types of filters, which are band pass, which can pass different like specific band, high pass, which pass only high frequencies and they cut attenuate the low part of the frequencies bands, and the low pass filters, which are actually pass all frequencies up to like particular cutoff frequencies. After this cutoff frequencies the signal starts attenuating. So this is what we're going to do today. We're going to experimentally see how we can actually attenuate the signal and see like how we can actually filter out the different types of signals, like different types of frequencies. So what we're going to start first, let's build like the simple basic filter, high pass or low pass. So as you remember, previously what we studied non-inverting and inverting type of op-amps. When we connect the input to minus, it's inverting type of op-amps. So if we connect the input to plus, it's non-inverting. So let's build right now the non-inverting pass filter. When we connect the input to the plus, and we have like feedback loop, resistor R1, R2. So let's try to make the low pass or high pass filter. So what difference between the high pass and the low pass? If you want to build a high pass filter, you have to connect the input, the capacitor in the series and the resistor in the parallel to the ground. If it's a low pass, we just have simply swap them. So put resistor in the series to the input and the capacitor should go to ground. Why it works like this? Because if we're gonna build, let's say, high pass, as we know, capacitors are shorted or open or shorted and easily can pass high frequencies, but they actually block DC or low frequencies. In these configurations, the high frequencies can pass to the amplifier, but low frequencies can be like attenuated. All frequencies component, they go either they stop by capacitor or they go to the capacitor, to the resistor, to the ground. And other way around, if we put resistor in the series and the capacitor in the short, all high frequencies go to the ground, and all low signals, like only low part of the frequency band of the signal goes to the amplifier. So let's try to build first the low pass filter. So as previously, so let's start doing non-inverting. So for non-inverting, what we have to do, we have to connect the input from the signal generator to the plus, and minus should be connected to the feedback loop with two resistors and to the ground. So what we do, plus the orange wire, remember orange line, it was from the oscilloscope or from the signal generator, function generator. So we put to the input 1K resistor, and we have to put also capacitor resistor in the short. So in our case, we put the capacitor to the ground. So this resistor goes to the put, but the second resistor, which is smallest one, 0.1 microfarad, to the ground. See, this is capacitor goes to the ground. So we now built low pass filter. Capacitor goes to the ground, and resistor goes to the input. And the minus should be connected to the ground through the two resistors. So minus goes to one resistor, which is connected to the ground. As we can see here, one resistor connected to the ground, and one should be in the feedback loop. And feedback loop resistor should be connected to the here. It goes from output to the 2K. So feedback loop resistor is 2K, and the resistor that goes to ground is 1K. And output goes to the oscilloscope, so we can see the output. So as before, we set signal generator. This time let's set signal generator to 100 Hz for initial frequency and 1 voltage peak to peak, and set this DC power supply to the 10 volt. Okay, so once you connect everything, let's try to like see what happens with the signal when we're gonna increase actually the frequency. See, so we should like actually observe how this low pass filter should actually attenuate higher frequency bands. So I'm going to start increasing from 100, 200. So let's see, 100, 200, 300, 400. As you can see, frequencies actually amplitude stays remain but slightly decreasing. So initially it was 3.24 voltage, increasing. It goes down, repeat down, down, down. As you can see, with increasing the frequencies, the amplitude of the output sinusoidal signal is decreasing. So as you can see, this configuration works as a low pass filter. So more, we're already in the 3 kHz. Amplitude goes down, down. So this is how the low pass filter is working. So let's now calculate the cutoff frequency of these configurations. In order to calculate cutoff frequency, there is a simple formula that everyone already knows. Cutoff frequencies can be calculated as 1 divided by 2p RC. R is resistor that goes to the input, and C is the capacitor that connected to the ground. So we connected the resistor with 1K, and we connected the smallest capacitor of 1.1 microfarad. So roughly it's going to be 1.6 kilohertz. So let's see what is the amplitude of output of 1.6 kilohertz. So one is 100 hertz, it's 3.2 hertz. But if we're going to increase to if we're going to increase the frequency, so as we calculate, it should be cutoff frequency at 1.6 kilohertz. So we go up to 1.6 kilohertz. So frequency went down to 2.26 volts. So from 3.24 to 226. So from 324 roughly 314, roughly let's say 224. So and as we should know, the frequency cutoff frequency is the frequency when a frequency goes from the initial frequency by 0.707. So if initial frequency was, let's say, R, then after cutoff frequency it decreases to times 0.707. So if we multiply 3.14, roughly 3.1, by 0.7, we should get roughly 2.21, and this is what we actually got. It means our low pass frequency is low pass filter, active filter is working. So let's now do, so what we did the low pass filter amplifier. Now let's do the high pass filter. For high pass filter it's the same structure, but just we need to swap the capacitor and resistor. Previously we had for low pass filter is resistor and capacitor. Now we're gonna see the resistor and capacitor. Resistor goes to the ground and capacitor goes to the input. So let's swap the input components. So previously we had input to the resistor and capacitor went to the ground. We just swap these two wires. So input orange wire goes to the capacitor, and the ground, resistor and ground goes to the ground, to resistor. So ground connected to resistor to connect to the ground, and the capacitor, the input goes to the capacitor. So immediately what we can see here, with a very low frequency like 100 Hz, signal very attenuated. This is how actually the high pass filter should work. It attenuates initial low frequencies, and after some cutoff frequency it's actually start passing the signal. As we already calculated before, for high pass and low pass filter, the cutoff frequency is calculated the same. So now it should be opposite. After 0.6 roughly kilohertz, signal should come to the full sinusoid. Actually not full, as we calculated, it should go to not 3 but 2.28 roughly. So let's see. So now we're going to increase the frequency from 1 Hz up to 1.6 kilohertz. Let's see.
As we can see, there is increase of frequencies, we have increase of amplitudes. So we go 1.3 kHz, 1.4, 1.6, and it's around 2.26 as it was calculated. Let's try to get the full signal. So we go very high frequencies, 2, 3 kHz, 4 kHz, 5 kHz. So it reached to the full of 3 volt, since it's non-inverting signal. So from 1 volt input we should get 1 plus 2 is 3. And this is how a high frequency pass filter is working.